Alrighty. So we've talked about divisibility, we've talked about mod, quotient, and modulus, those kinds of things. So this naturally leads us, the next thing to talk about is primes. So who can tell me what a prime number is? Yeah?
It's the number that does not have two numbers that multiply to make it in the integers or natural.
So there's no two numbers in the integers that multiply to make that number? Okay. What do y'all think? Does that seem like a good definition, or is there a different definition that, like?
I've always heard it described as it's a number that's it's only divisible by one in itself.
So it's only divisible by one in itself. Okay. So are those the same, or are they different?
I definitely did not describe that.
Okay. Anyone else have another way you think about what a prime number is? I'm assuming that you all have heard about primes like in elementary school, right? So, and you probably know like which numbers are prime, but maybe you've never thought carefully about how to formally define it. I don't know. So anything else? What's a prime number? How do you think about that? So the definition that Strauss gave, he said there's no two numbers that multiply to it or something, right? And I think I understand where you're going with that, but logically what you said, right? Like, I mean, 7, there's 1 times 7 that makes 7, right? So you have to say a little bit more than that. Yeah. And so what Taylor said is often the definition you hear, right? It's a number that's only divisible by 1 in itself, right? But we have to be a little bit more careful than that too. So for example, is 1 prime? Anyone know?
Isn't this a big debate?
It's not a big debate, but it is open to, like, in some sense, there's not necessarily a right answer, but there is an answer that's more useful than the other. Malcolm?
I feel like it's not, because I think that any number multiplied by 1 can make itself, so I feel like that shouldn't count to part of what makes it prime.
Yeah. So you're kind of, so yes, you're right, and I think you're referring to what we're going to talk about in a minute about how we can kind of take numbers and break them down into multiplying a bunch of primes. And if you count 1 as a prime, then you can always say times 1 times 1 times 1, and it's kind of stupid. Like, what, you don't really need to add that on. So yeah, usually we don't count 1 as a prime. But if you just take the definition as it's only divisible by 1 in itself, well, 1 is only divisible by itself, and which is also 1. So, right, it would fit that definition. But we usually say, except not 1. 1 is special. So I'll write it like this. Say an integer p greater than 1 is prime if and only if the only divisors of p are 1 and itself. And so I put here the fact that I wrote p greater than 1, right? That encodes this restriction I just talked about, that we don't consider 1 a prime. So it can't be 1, it has to be bigger than that. But otherwise, subdivision. And I think it's worth thinking about how would we write this down formally in formal logic. So we'll say, okay, what does it mean for p to be prime? Well, first of all, p has to be greater than 1. And what? going to give you, I don't know, 30 seconds or a minute or something. Turn to some neighbors, chat about how would you, like this idea that the only divisors of P are 1 in itself. How would you write that down in like, formal propositional logic? Go ahead and chat.
If and only if it's the double error rate
Yeah.
that divides.
Which you don't have to say.
No, or would it be like divided by its random bit? Double-headed arrow, that looks like that. There we go. I don't. I'm gonna go.
All right, let's hear some ideas. And there's not one right answer. There's multiple possible ways that we could encode this. Ideally, we could show that they're all logically equivalent, right? But kind of different ways to think about it. Taylor, did you?
No, wait, I'm not done with my answer, never mind.
That's okay. What were you kind of thinking along the lines of? We can turn it into something good.
So we thought the if and only if was the double-headed arrow.
Okay.
And so we thought the P and then the divisor one double-headed arrow like true. So like
Okay. Yeah. I mean, so we're talking about this if and only if part. So the if and only if part is really just saying like we're saying kind of being prime is defined as if and only if blah blah blah. So the part we're writing down here, the if and only if is not really part of this. I guess maybe this equals as an if only if. Maybe I should have written it as a if only if or a triple equals. I don't know, but we're just defining what it means to be prime. Other ideas? How might you encode this? And even if you don't know the whole thing, like how might you start? Nina?
Like there does not exist when you say A and B, such that A times B equals A and B not included.
Okay, good. So something like it is not the case that there exists A and B integers such that what? So A times B equals P and what?
A and B not included.
Oh, and A is not equal to P and B is not equal to P? What do y'all think? So we clearly need this part. If we don't have this part, this is just going back to, this is basically, I think, what Joust said at the beginning. It's like, oh, there's nothing that multiplies to it. Well, but, we could pick A and B to be 1 and P, so that, but it's saying, no, Nina is saying there don't exist numbers that multiply to it where neither of them is equal to P. So if you have to get to P, but neither of those things can be P, then you're going to have some kind of non-trivial multiplication. But you can't pick them to be 1 either, because like they can't both be 1. That wouldn't work, right? Yeah, I think this works. That's good. Did anyone think of a different way to, or had some different ideas about how where they might go with it, even if it's not complete? Yeah, Josh?
There is not some in the natural numbers greater than 1 less than P that divides P.
Oh, okay, good. Yeah, so you're saying like, okay, P is greater than 1, and there does not exist N. You said a natural numbers.
Right? Is prime supposed to take, prime can take negative numbers, but technically is negative numbers be prime?
Good question. Usually we don't consider negative numbers prime. Yeah. I mean, yeah, I guess I haven't. That's this p greater than 1 is taking care of that.
Oh, yeah.
Right. So does not exist a natural number n such that you said n is.
N is greater than 1, less than p.
Oh, okay. So n is greater than 1, and n is less than p, and n evenly divides p. Okay. Yeah. Good. I mean, if you think hard, or not, you don't think that hard, but if we think about what the definition of divisibility means, like these are, I think it wouldn't be too hard to show that these are the same, right? These are kind of saying the same thing. This is talking about like the two numbers that we multiply to get p. This is talking about only one of them, but if p is divisible by n, then there has to be some other number that we multiply n by to get p, right? Saying the same thing. Here's a very different way we could do it, which maybe is a little harder to think about, but in some sense corresponds more directly to the way we phrase the definition, right? The only divisors of p are 1 and itself. So what I want to say is if a number is a divisor of p, then it has to be either 1 or p. So we could say prime p is, okay, again, p is greater than 1, and for all, I'll say d, like divisors, right? If d divides p, then d equals 1 or d equals p, right? So it's possible to have a divisor, but the only way you can have a divisor of it is if that thing is actually either 1 or p. These are all equivalent. Actually, yeah, this one. So these two are probably the closest. Like if you take this knot and you start pushing it through using De Morgan, right, this will turn into a for all. And then this stuff will turn into something with some knots and ors, and then you can turn that into an imply. I think you can actually not, it's not too hard to turn these into each other. So, all right, moving on. Okay, so for example, right, we all know this, I think, 2, 3, 5, 7 are prime. Right, 6 is not prime since 2 times 3 equals 6. Right. And also I should say, right, a number greater than 1, which is not prime, is called, and you know what, I'm going to be really honest with you. I'm not sure whether this is pronounced composite or composite. And you, like, how did I get through 40 years of life and not know that? But I don't know, somehow, I don't know. So say it however you like. I'll probably say one of them, but I don't know. If, you know, if you say it the way that I say it and one of your other math faculty laughs at you for pronouncing it wrong, then don't tell me, okay? And note, right, 1 is special. 1 is neither prime nor composite, or composite, whichever. Right, and you might think that's sad that 1 gets left out, but actually it's because 1 is super special, right? 1 is a unit. It's the multiplicative identity. It's the number that when you multiply by it, nothing happens. That's a very, very special property, and so it's kind of in its own special category by itself, right? Okay. So theorem, which we're not going to prove today. You've probably heard this theorem before, or at least implicitly. Maybe you haven't heard it stated this way. So this is called the fundamental theorem of arithmetic. So it's obviously pretty important. People think it should be called the fundamental theorem. Here's what it says. Every positive integer can be factored into a product of 0 or more primes. Okay, I'm not quite done with the statement of the theorem, but let me pause there for a second. So notice I said every positive integer, so that actually includes 1, right? 1 is a positive integer. And notice also I said a product of 0 or more primes. What is a product of 0 primes? Yeah, so this is why I included 1, because if you take a product of nothing, then you should get 1, not 0. Why is that? Well, there's a bunch of different. It's one of those things, and we've seen things like this before. Like, for example, should the empty set count as a subset of things? Should like a set count as a subset of itself? You could answer it either way, but one of them is going to work out a lot more nicely than the other, right? You're free to define it however you want, but it's sort of like, it's kind of like if you're trying to go from point A to point B, and you're like, if I want to get from here, to the calf, should I go like, should I walk this way, or should I like, catch the city bus to take me over there? It's like, well, technically you could do whatever you want, but one of them is probably going to work out a lot more nicely for you, right? It's that kind of situation. And it's the same thing here. What is a product of 0 things? I mean, in some sense, we can define it to be whatever we want. There's no like back of the book where we look up the answer to the universe and it tells us what the answer is supposed to be. But it works out a lot more nicely if we say a product of 0 things is 1, because 1 is the multiplicative identity, right? When you multiply 1 by something, nothing changes. So, imagine like writing a program to multiply all the things in a list, right? What do you do first? You set your variable to 1 to start, and then you start iterating through the list, and you start multiplying things by it. And if there's nothing in the list, then it's just still 1, and that's what you return, right? Okay, so I'll put that here. Note, a product of 0 primes is 1. And then I'll say the other interesting part of this, moreover, maybe I'll say this. There's a bunch of different equivalent ways to say this, but I like saying it this way. Moreover, this product, this product of primes is unique if the primes are listed from smallest to biggest. What do I mean by that? I mean that, okay, so obviously 6 is 2 times 3 is 3 times 2. 2 times 3 and 3 times 2 are, literally, I just said different things, but we consider them the same because we really don't care about what order the primes are in, because multiplication is commutative, right? We know that if we switch the order of multiplying things, it doesn't matter. So we'll just say, look, let's just say you're going to list the primes from smallest to biggest. Okay, then what we're saying is there's only one way to write 6 as a product of primes. 2 times 3. That's it. Now, you're all probably familiar with this idea, and you're probably so familiar with it that you don't realize how astonishing it is. So, like, who's to say that, maybe there's some big number, like, 1,472,629, and actually, it's equal to 47 times 383. Those are both primes, but also it's equal to 53 times, 247. Right? There's 2 different ways to write it, just multiply primes and get that big number, right? Why not? Well, it turns out, no, there's not. Like any number, you can break it down into primes, and there's exactly one way to do that. I was thinking of some examples earlier. Now I'm trying to remember what the examples that were I came up with. A situation where there's a way to break things down into parts, but like there's multiple different ways to do it. I had a good example. What was it? Well, so certainly with addition, right? Like if I say, well, 10 is 2 plus 8, but it's also 3 plus 7, right? Those are two different ways to break down 10 into, if you're adding up numbers. Anyway, okay. If I think of a good example later, I'll say it. But yeah, it's sort of, it makes sense that we can multiply, things to get, it's like, if there's such a thing as primes, then we can multiply them to get bigger numbers. But who's to say that there couldn't be like multiple different ways to break down some number into primes? But it turns out that there's not, and that's a really important and helpful fact. And I guess I will say that when you generalize to other systems of numbers, so for example, if you start thinking about like how does this relate to say complex numbers, it turns out this doesn't work with the complex numbers. Like with complex numbers, there is a way to define things that kind of act like primes, but when you try to factor things, like can be multiple ways to do it. And so this theorem is not true for other kinds of numbers. So proof, we'll do this later. And we need induction. I think I've said that for several things so far. It's like, well, we'll prove this later because we need induction. Okay, and here's another theorem that we're gonna do as an example and actually do a careful proof of. And this is again is one of those things that maybe seems obvious, but it's a useful fact to keep in mind. So here's the theorem: if n, if n is composite, then it has a prime divisor less than or equal to the square root of n. Right, so this is saying, look, if you give me a number, so if a number is prime, then it's prime, right? But if it's composite, then that means that there's some way to write it as a product of primes, and I'm saying at least one of those primes has to be less than or equal to the square root of n. Now, the first thing is it's actually really interesting to figure out how to write this out in formal propositional logic, because there's actually quite a lot of stuff that's packed into this one sentence, because we've got like a bunch of adjectives tacked onto each other and stuff. So, okay, first of all, it's talking about n, and it didn't say what n is, so it's a for all, right? We're really saying something about for all n. So for all, we'll say for all n, which are positive integers, because we really define like being composite or prime, that's all defined for positive integers, right? So if n is composite, okay, so that's easy. So I'll just say composite n implies, okay, so that's the easy part. Or I could say not prime n. That would be the same thing. So then it has a prime divisor less than or equal to square root of n. How would I start? How would I write this down? Tyler?
Would you do like? So would you do like n and then like the divisor, n divided by p?
Okay, what's p?
Oh, yeah.
So sure, but if we want to, what is okay? Sounded like someone was calling me. I don't know. Yeah, so if we want to talk about another variable p, right? Maybe we haven't talked about it in these terms, but how do we make new variables? That's a weird way to phrase it, but
For all.
yeah, exactly. So actually, the only way we have to make new variables is for all or exists. That's it. Those things like kind of create a variable and say, here's a thing you can talk about now, and we're saying that either this exists or this is true for all things. Yeah. So which do we want?
There exists because it says there
Yeah,
has.
exactly. It has, right? There exists. Okay, so there exists. We'll call it P. We'll say P is also a positive integer, such that what? So what has to be true about P? It's prime. I heard someone say that. Yes. So P is prime. What else has to be true about P? Mara? P, right. It is a divisor of n. So it says it has a prime divisor. That means, so we'll say and P divides n. Anything else? It's less than or equal to square root of n. Yeah. So like basically these three, this isn't exactly a word, but it's like, so, right, prime, divisor, less than or equal to n, like each one of these things turned into a property that we handed together. So English gives us an economy of, you can just like stack adjectives on top of each other and stuff like that, but often if you stack a bunch of adjectives, it really corresponds to saying a bunch of ands, right? If you're like the big, green, mean dog, right, you're really saying three things that are all true about the dog, right? Or you're claiming they're true. There exists a dog such that. Okay, let's prove this. No, you know what? I'm going to start on here. Proof. All right. Well, let's say let n be an arbitrary positive integer, and suppose n is composite. Well, if we suppose it's composite, then, according to our definition of prime, and composite is not prime, actually, if we look at, I think this was, maybe that was Nina's definition, but this one is the easiest to negate. If we just say, well, okay, for to be composite, it still has to be greater than 1, so forget that part. But if we just negate this, it's like, oh, we just get rid of the dot. And so this is the definition of composite right here. There is actually, yeah. Oh, is this? Whatever. Yeah. Actually, no. This it doesn't matter whose it was, but these are all good. I think this one is going to be the nicest for our proof. So really, what does it mean for something to be composite? Well, it means there exists A and B such that they multiply to give you that thing, and but neither of them is equal to P. So, okay. Then there must exist A and B such that A times B equals N, and we'll say 1, right? They're in between 1 and N. So neither of them is equal to 1, neither of them is equal to N. They're somewhere in between, and we multiply them and get N. Okay. So I'm going to do something called a proof by cases, which we haven't really talked about explicitly, but basically it's just saying, let's kind of take the current situation. We're going to split it up into a few different cases. And as long as they cover all the possibilities, then, and in each case we can show why the thing is true, then we're good, right? Really, I'm just going to split this into two cases. So I'm going to say, first of all, if A and B are both greater than square root of n, well, what would happen if A and B are both greater than square root of n? Then A times B would be greater than square root of n times square root of n, which is n, right? But we assume that AB is equal to n. Like, they can't both be bigger than the square root of n because their product then would be too big, right? Which is not possible since AB equals n. Okay, so really what we just showed is that case can't happen. So therefore, at least one of A or B must be less than or equal to square root of n. I'm just going to say suppose it is A. Now you're like, well, but we don't know that it's A. It could be B. Yes, it could be, but because there's nothing really different about A and B, if you're like, okay, actually it's B. B is the one that's less than or equal to square root of n. I'm just like, fine, just switch their names. I don't care, right? So really, it's fine if I just say, yeah, just suppose it's A. Sometimes you'll hear mathematicians say without loss of generality, which means I'm going to assume something more specific, but if you think about it, it really doesn't matter. And so it's fine to just think about this case because really that kind of will stand in for all the possible cases. Well, so what are we trying to show? Remember, we're trying to show that there is something that's prime that divides n and that is less than or equal to square root of n. So right now, our A, the number A that we have, like how many of these things does it satisfy? Which one? It's less than or equal to square root of n? Yes. Does it satisfy any of these other things? It does actually satisfy one more. Remember how did we define A? So where did we got A from this assumption that there have to be, A and B that multiply to give us n. So actually we also know that A divides n because it's A times, like n is A times B. We don't know that it's prime, right? There's nothing that says it has to be prime. So we'll say we know that A divides n since AB equals n. However, we don't know whether A is prime. Okay, but we're almost there because the fundamental theorem of arithmetic says, right, that, well, it might not be prime, but we can factor it into a product of a bunch of primes. All of those primes, well, they divide A, so they must divide n, and they're also smaller than A, so they're smaller than square root of n. So, but by the fundamental theorem of arithmetic, A is a product of primes. And I'll just say let P be one of those primes. Then P is less than or equal to A, which is less than or equal to square root of n. And P divides A, which divides n. And therefore, P, I'll just say P is a prime, or I'll say, okay, well, how do I say this? maybe I'll just, it's a little awkward, but whose existence we wanted to show. Right, the thing we were supposed to show was that there exists a number which is prime and divides n and is less than or equal to square root of n. And we now have this p and it satisfies both those things. Right, because less than or equal to is transitive and divides is transitive, so. Okay. So let me show you something called the sieve of Eratosthenes. And you'll see why I'm showing you this. Like, it's actually kind of a nice application of this thing we just proved. So here's the idea. And this was, it's named for Eratosthenes, who is some ancient Greek guy, I don't know. And so I'm going to list,
Yeah, you have to do all the numbers now.
I'm only going to go up to like, it's nice if you do it like a 10 by 10 thing, but I don't want to write all those, so I'm not going to. You can make it yourself, or you can look in the lecture notes. One more. 31, 32, 33, 4, 35. So here's the idea. And actually, you don't have to draw the numbers in a square. You could just have them in a big list. Drawing them in a square is nice for reasons that you'll see in a minute. But here's the idea. So 0 and 1 are not prime, right? We're trying to figure out what numbers are prime. So I say, all right, 2 is the next number in my list, so it's prime. So I'm going to, we'll say orange is prime. So I'm going to circle 2, or square it, I guess. And so now, since 2 is prime, anything else divisible by 2 is not prime. Right? So like 4 is not prime because it's 2 times something. So I'm going to cross out all the even numbers, right? So all of these I'm going to cross out, all of these I'm going to cross out, all of these I'm going to cross out. Okay. And now I go on. So 3 is the next number in my list. So 3 is prime. Let's use a different color for that. We'll use blue. Now I'm going to cross out all the multiples of 3 because, again, if 3 is prime, anything divisible by that is not going to be prime. So there's a bunch in this column here. And I think these are also all, they're already crossed out, but might as well draw that right. Okay, 4 is already crossed out. It's not prime. 5 is the next number. So we'll do, so 5 is prime. I'm going to cross out all the multiples of 5. So if you think about it, multiples of 5 are along diagonal lines like this. So there's those, and also actually this one. I think that's it. I mean, technically, I guess I could like draw a little line through 0, but whatever. Now, here's the cool thing. We're going up to 36, right? So the square root of 36 is 6. So any number up to 36, if it's composite, then it has to have a prime divisor that's less than or equal to the square root of 6. Or less than or equal to the square root of 36, which is 6. So at this point, we can actually stop and say, look, like anything else that's on here, if it had a divisor, then we would have already crossed it. We would have already found it. Right? You know, like 22. 22 is, well, it's divisible by 11, but it's also divisible by 2. So anything that's divisible by something is going to be divisible by one of these numbers in the first, on the first row. So at this point, I can just stop and I can just circle all the remaining numbers and say these are all prime. I don't even have to do anything. I just know these are prime. There you go. That's all the primes up to 36. And you can do this, if you think about it, if you made a 10 by 10 square, right, the only other prime up to 10 is 7. And so you would, if you made it 10 by 10, you just have to do one more step where you cross out all the multiples of 7, and you would now have all the primes from 1 up to 100. So it's actually not that hard to figure out all the primes, you know, up to some pretty big number, you only really have to do work up to the square root. And this is actually, I mean, it's kind of fun to do it with pencil and paper, but it's actually a good way to generate primes on a computer. So if you want to make a big table of all the primes up to some limit, and you want to be able to quickly look up any number to see if it's prime, right? You just make a big array and you kind of like, you do this procedure, and you can stop once you get to the square root, and you now have your big table of all the primes. So I guess this is like an example of ancient Greek technology that we're still using. Also, if you do this for bigger squares, the patterns of like which things get crossed out looks really cool. So I recommend you try it. Alrighty. One more thing, also courtesy of the ancient Greeks. Theorem, there are infinitely many prime numbers. Maybe you already knew this fact. Maybe you haven't thought about why it's true. But a priori, there's not necessarily any reason this has to be true. I mean, like it could be that there's just like, there's 29 different primes. That's all of them. And then any number in the whole, I mean, like, even though we know the fundamental theorem of arithmetic, it could be like, well, any number, really big numbers, you just have to include lots of copies of, some of those 29 primes in different combinations. So it doesn't necessarily, like, we could have a finite number of primes and multiply more and more of them together to get all the numbers, right? That's conceivable. It turns out that's not true, but a priori, we wouldn't know. But let's prove it. So we're going to prove this by contradiction. So proof by contradiction. That is, we're going to say suppose. So we're going to suppose this is false. That is, suppose there are only finitely many primes. And we're going to call them P1, P2, ... up to like PK. I don't know. So this is all the primes that exist. And then we're going to consider, I'm going to define a number called Q. I don't know why I'm calling it Q. How am I going to define Q? I'm going to multiply all the primes. And then I'm going to add 1. This might be a very large number. That's okay. But, according to my supposition, this number is the product of all the primes plus 1. And so I want to think about the fundamental theorem of arithmetic tells us that we can factor this into a product of primes, but let's think about which primes those could be. So is Q divisible by P1? Could it be divisible by P1, I guess I'm asking.
P1 is P2 and 2.
Yeah, okay, so let's say P1 is 2, right? This is actually the form 2 times a bunch of stuff plus 1. So it's odd, right? It's not divisible by 2. It gives a remainder of 1 if you divide it by 2, right? What about P2? What if we divide it by P2? Is it going to go in evenly, or are we going to get a remainder? We'll get a remainder of 1, right? Because it's P2 times all this stuff plus 1, right? So the way I've defined it, each one of these primes will not be divisible by any of these primes. It's always going to give a remainder of 1 when you divide it by each one of these. So Q cannot be divisible by any of the primes, since I'll say it would give a remainder of 1. Right, but the fundamental theorem of arithmetic tells us Q is a product of primes, right, but none of which are on our list, right? So therefore, this is a contradiction, right? The contradiction is we assumed we had all the primes, but then we just used those primes to create a number that is divisible by some other primes that weren't on our list in the first place. And so that doesn't make sense, right? We didn't actually have all the primes in the first place. Right. So another way to think of this is if I give you some primes and I'm like, find me a different prime that's not on this list, you could multiply them all together, add 1. That thing you get might not itself be prime, but if you factor it, you're going to get a bunch of primes that were not on the original list, right? Now, this is not really a practical way to find primes because this will get very large, right? Anyway, and just as a fun aside, I will say that so there's infinitely many primes, so there's primes that are as big as you want. So there's no largest prime, right? However, there is a particular number which is the largest prime we know of. That is, it's the largest number that we can point to specifically and say we know that this number is prime. We know that there are bigger ones that are prime, but we're not sure what they are, right? That number, so the biggest known prime is, I'm going to write it down for you, 2 to the 82,589,933 minus 1. This number has about 24 million digits if you print it out in decimal, right? If you like printed a book with this number in it, say maybe like 100 digits per line and 50 lines of digits per page, it would require about 5,000 pages. So probably like imagine like a 10-volume set of books, on a shelf like this, just to print that number. The reason that we know that is because for numbers of this form, specifically 2 to some power minus 1, we know of a special algorithm that can check whether it's prime much more quickly than other numbers of that size. So the biggest known prime is always probably going to be of this form. Anyway, that was found about 3 or 4 years ago, I think. But people are looking for bigger ones. Alrighty. I will see y'all on Friday.
In the time of big class, you should tell us about the algorithm.
The algorithm?
I'm not sure the one goes about
Yeah, that's our programming language. Find a new prime.
No. It's there's some pretty interesting and sophisticated math that goes into it.
Aren't they used in cybersecurity?
What was that?
Are they used in cybersecurity?
Or what?
Isn't the importance of finding like ever larger primes for like cybersecurity?
No.
purposes? Oh.
So, not directly. So like that prime specifically would probably not be very useful for security stuff. A, it's actually way too big to be practical for anything. And B, it's so special that probably like all your things would break because it's like, if you use a prime with these special properties, then there's a way to break it, right? No, so for doing security stuff, you often want large primes because you want to be able to multiply things and then have factoring it be hard. But it turns out that to do that, you don't do something like this. You just like pick a big number and you check whether it's prime or not, which we know how to do efficiently, even though we can't factor it efficiently. It's possible to check whether a number is prime without factoring it. It turns out that's easier. So you just generate a big number, and you're just like, is it prime? Nope. Okay, try another one. And on average, you might have to generate like 50, but it's not a big deal. Just find one that's prime, and then. But more like, when I say big number, more like 500 digits, not like 24 million digits.
You're telling me all your passwords are an algorithm that just makes prime numbers?
I'm not telling you that.